In the grand narrative of scientific thought, certain images possess a power that transcends their immediate context, becoming emblems of an entire intellectual epoch. One such image is the ceaseless, frantic dance of a pollen grain suspended in water, observed by the botanist Robert Brown in 1827. This motion, at once aimless and persistent, was a microscopic glimpse into a universe governed by forces that defied the deterministic elegance of Newtonian physics. It was a world of perpetual agitation, where causality was hidden within a veil of countless unseen collisions. For decades, this Brownian motion remained a curiosity, a puzzle on the periphery of physics. It took the annus mirabilis of Albert Einstein in 1905 to provide a physical theory, and the independent work of Marian Smoluchowski to explain this jittery choreography as the result of impacts from thermally excited water molecules. Yet, even with a physical explanation, a deeper challenge lingered for the language of mathematics itself. The challenge was to move from a statistical description of the aggregate effect to a dynamic moment-by-moment account of a single random trajectory. The task was to write the equation of the dance itself. This endeavor fell to the American mathematician Norbert Wiener in the 1920s. He constructed the first mathematically rigorous model for Brownian motion, a construction now known as the Wiener process. This achievement was a triumph of the new and powerful tools of measure theory, and it gave mathematicians a concrete object to study, a continuous random path. The Wiener process is a function of time, let us call it W sub t, that captures the position of our dancing particle. It is continuous, meaning the particle does not teleport. It moves from one point to another by traversing all points in between. Its increments over disjoint time intervals are independent and normally distributed. Herein lay the profound and beautiful paradox. Wiener had given the world a perfect mathematical model of pure continuous noise, yet in doing so he had created a monster. This path, while continuous, is nowhere differentiable. At no point does it possess a well-defined velocity. If one were to zoom in on a segment of a smooth classical curve, like the arc of a parabola, it would eventually appear as a straight line. Its local behavior is simple. Attempting to do the same with a realization of the Wiener process is an exercise in profound futility, akin to asking for the precise street address of a cloud. Each magnification reveals more jaggedness, more complexity, more erratic behavior, a property of self-similarity that is both fascinating and deeply troubling for classical analysis. The consequence of this non-differentiability was catastrophic for the existing mathematical toolkit. The entire edifice of calculus, built by Newton and Leibniz to describe rates of change, rested on the assumption of local smoothness. The derivative, the very heart of differential equations, was undefined. The language that had so masterfully described the orbits of planets, the flow of heat, and the propagation of waves, fell silent. It was as if mathematicians had been given a new fundamental element of nature, but found that all their instruments were calibrated for a different reality. The state of probability theory in the 1930s, following the axiomatic revolution of Andrei Kolmogorov, had provided a solid foundation for the existence of such processes. The question was what to do with them. How could one model a system whose evolution was influenced by this kind of continuous violent randomness? How could one formulate, let alone solve, an equation of motion like dx equals a x dt plus bx dw, where the system's change is driven partly by a smooth deterministic drift and partly by a noisy Brownian kick? This was the great unsolved problem that loomed over the field. It was into this intellectual landscape that a young Japanese mathematician, Kiyosi It, entered in the late 1930s and early 1940s. Working in a nation increasingly isolated by war, Ito was at a significant remove from the major centers of mathematical research in Europe and North America. This isolation, however, may have cultivated a unique and unburdened perspective. Immersed in the works of the French school of probabilists, particularly the profound and almost mystical insights of Paul Lévy, Ito became fascinated with the intricate structure of stochastic processes. He recognized that the impasse was fundamental. The challenge was one of language. The Wiener process was not a poorly behaved function to be tamed or approximated by smoother ones. It was a new kind of entity that demanded its own calculus. In a series of papers culminating in his seminal 1944 publication on stochastic differential equations, Ito laid the foundations for this new language. His central insight was to reconsider the meaning of an integral. The classical integral of Riemann is a method of summing up areas of infinitesimally thin rectangles. A more general version, the Riemann-Stieltjes integral, allows one to integrate one function with respect to another, 4g This works beautifully as long as the integrator function, g of t, is of bounded variation, meaning its total up and down movement is finite. The Wiener process, with its relentless fractal-like oscillations, has a variation that is almost surely infinite. The old tools simply shattered when applied to it. Ito's conceptual leap was to define a new type of integral, one constructed specifically for the unruly nature of the Wiener process. He defined the integral orgat dwt as a limit of sums much like the Riemann integral. The revolutionary move was in a subtle but critical choice of convention. In each small time interval of the summation, from t sub I to t sub I plus 1, the function in t would be evaluated at the beginning of the interval, at time t sub I. This non-anticipating property, as it is now called, is a profound statement about causality. It means that the influence of the random kick dwt over an interval can only be weighted by information available at the start of that interval. One cannot know the outcome of a random fluctuation before it has occurred. This seemingly innocuous choice ensured the resulting integral was well defined and possessed the properties necessary for a robust theory. With this new integral, Ito provided the missing cornerstone. He had forged the first tool of a new calculus. A calculus designed not to ignore randomness or to average it away, but to incorporate it as a fundamental, dynamic element of the system. He had begun to articulate the grammar of chance, providing a rigorous way to understand the evolution of systems buffeted by the ceaseless storm of microscopic uncertainty. The path was now open to explore the consequences of this new formulation, leading directly to the single most important computational tool in the entire field. A new chain rule for a world where the future is written in the language of probability. The intellectual edifice Ito had begun to construct required a new kind of mechanical rule, a fundamental theorem of change for a universe governed by chance. The familiar tools of Newton and Leibniz, elegant and powerful as they were for describing the smooth deterministic arcs of planets and projectiles, proved remarkably fragile when confronted with the jagged, unpredictable path of a random process. The classical chain rule, which allows a mathematician to calculate the change in a function of a changing variable, rests on an assumption so basic it is rarely stated that small changes, when squared, become infinitesimally smaller and can be safely ignored. The change in a function f of x, written as df of x, is simply the derivative f prime of x, multiplied by the change in x, or dx. Any terms involving dx squared or higher powers vanish into irrelevance. This bedrock assumption of classical calculus is catastrophically violated by Brownian motion. The path of a particle undergoing such a process is, in a formal sense, nowhere differentiable. Its trajectory is a fractal landscape of infinite roughness. The change in its position over a small time interval, dt, which we denote dw sub t, does not behave like a classical differential. Its magnitude is proportional to the square root of dt. This is a direct consequence of the statistical nature of the process. The variance of the displacement grows linearly with time, meaning the standard deviation, a measure of the typical size of the fluctuation, must grow with the square root of time. This single property shatters the classical world. If dw sub t is of the order of the square root of dt, then its square, the quantity dw sub t squared, is of the order of dt itself. It does not vanish, it persists as a first-order term, a Taylor expansion of a function of a stochastic process, say f of w sub t, suddenly contains a second derivative term that refuses to disappear. The old calculus was built for a world of smooth curves. Ito was faced with the challenge of building a new one for a world of infinite zigzags. His first monumental step was the formal construction of the integral that now bears his name. The problem was how to give meaning to an expression like the integral of some function g of t multiplied by the infinitesimal random kick dw sub t. The standard generalization of the familiar Riemann integral, the Riemann-Stieltjes integral, falters here. It requires the integrator, in this case the Brownian path w sub t, to have what is known as bounded variation. This is a technical way of saying that the total up and down distance traveled by the path must be finite. A Brownian path, with its relentless microscopic oscillations, has unbounded variation. Attempting to define an integral along such a path using classical methods leads to ambiguity and contradiction. The value of the integral depends entirely on how one chooses the evaluation points within the infinitesimal subintervals. Ito's genius was to resolve this ambiguity with a choice that was both mathematically rigorous and philosophically profound. He defined his integral as the limit of a sum, much like a Riemann sum. But for the function g of t, which determines the magnitude of the investment in the random process at each moment, he imposed a crucial condition: the function must be non-anticipating. In constructing the sum, the value of g of t over a small time interval from t to t plus delta t could only be evaluated at the beginning of the interval, at time t. One is forbidden from peeking into the future. You cannot decide how much of a random stock to buy based on the price fluctuation that is just about to happen. This non-anticipating constraint, which he called an adapted process, eliminates the ambiguity. By systematically choosing the left end point of each time interval, the integral acquires a single well-defined value. It becomes a martingale, a technical term for a process whose expected future value, given all past information, is simply its current value. It represents a fair game. With a well-defined integral, Ito could turn to the central problem: differentiation. How does a function of a stochastic process change over time? The answer is his celebrated lemma, a result of such fundamental importance that it has been called the chain rule of random chance. Ito's lemma is the direct and beautiful consequence of the strange new arithmetic he had uncovered. It arises from taking a simple Taylor series expansion of a function, f of x sub t, where x sub t is a stochastic process, and refusing to discard the second-order term. Let us consider a general stochastic process, x sub t, whose change dx sub t is composed of a predictable drift component proportional to dt and a random diffusion component proportional to dw sub t. When we ask how a function of this process, f of x sub t, changes, we expand it. The first-order change in f is its partial derivative with respect to time, plus the partial derivative with respect to x multiplied by the change in x, or dx sub t. This looks much like the classical multivariate chain rule. The revolutionary step comes from the second-order term, 1/2 times the second partial derivative with respect to x, multiplied by dx sub t squared. In a deterministic world, this term would be discarded. In Ito's world, it is the main event. Since dx sub t contains a random part proportional to dw sub t, the term dx sub t squared will contain a term proportional to dw sub t squared. And as Ito had established, this is equivalent to dt. The infinitesimal randomness, when squared, alchemizes into an infinitesimal, yet purely deterministic, passage of time. The result is a formula of astonishing power. The change in f of x sub t, or df, is given by the classical terms, plus an additional, non-classical term, 1/2, times the second derivative of f with respect to x, times the variance of the process, all multiplied by dt. This is Ito's lemma. It is the stochastic analog of the chain rule, and it provides the engine for all of stochastic calculus. The additional term, often called the Ito correction term, is a mathematical manifestation of a deep physical truth. For a smooth deterministic path, moving from one point to another is a simple displacement. For a random jittery path, the very act of moving, the ceaseless oscillation, contributes to the change in the function's value. The convexity of the function, captured by its second derivative, determines how this jitteriness translates into a net drift. A convex function, one that curves upwards, will gain more on its upward fluctuations than it loses on its downward ones, resulting in a net positive drift, a gift from pure volatility. Ito had created a complete self-consistent system for manipulating stochastic differential equations. He had provided the tools to differentiate and integrate functions of random processes, to change variables, and to solve for the evolution of systems that were previously beyond the reach of rigorous analysis. This lemma became the foundational computational device, the key that would unlock the quantitative study of nearly every field touched by randomness. He had forged a mathematical language capable of describing the dynamics of uncertainty itself, preparing the ground for a revolution in how science and finance would come to model the world. A mathematical framework of such elegance and power, once forged, seeks a world to describe. In the mid-20th century, the domain of economics and finance presented a landscape of tantalizing complexity, a world governed by chance yet desperately in need of quantitative order. For decades, economists and financiers had grappled with the erratic dance of market prices. Their models were often static, deterministic, or reliant on discrete, stepwise approximations of what was clearly a continuous, fluid reality. The essential problem was one of dynamics under uncertainty. How could one rationally value a promise on a future event, like a stock option, when the path to that future was a thicket of random fluctuations? The existing mathematical arsenal was simply unequal to the task. It could describe states, but struggled to capture the process of becoming. The stage was thus set for Ito's calculus to make its most celebrated, and for some, most notorious, entrance. The specific challenge that would showcase its power was the pricing of financial derivatives. A European call option, for instance, is a contract giving the holder the right, though not the obligation to purchase a specific stock at a predetermined price, known as the strike price, on a specific future date, the expiration date. Its value is clearly contingent on the price of the underlying stock. If, at expiration, the stock price is well above the strike price, the option is valuable. If it is below, the option is worthless. The central mystery was how to assign a fair price to this contract today, given that the stock's future price is unknown. The first crucial step, taken by pioneers like Paul Samuelson and later refined by Fisher Black, Myron Scholars and Robert Merton, was to find a plausible mathematical model for the stock price's random walk. They proposed that the stock price follows a process known as geometric Brownian motion. This model is expressed as a stochastic differential equation. It states that the infinitesimal change in the stock price, let us call it ds, over an infinitesimal time interval, dt, has two components. The first is a deterministic drift term given by mu times s times dt, where s is the current stock price and mu represents the average rate of return. The second is a random diffusion term, sigma times s times dw sub, where sigma is the stock's volatility, a measure of its jaggedness, and dw sub t is the increment of a Wiener process, the unpredictable pulse driving the system. The geometric nature of the model, where the changes are proportional to the price S itself, carries the profound and practical implication that a stock price can never become negative. With a rigorous model for the underlying random process in hand, the path was clear for the decisive insight of Black, Scholes and Merton. They imagined an investor creating a portfolio. This portfolio would contain a specific quantity of the underlying stock and a position, in this case a short position, in the option itself. The value of this portfolio would of course fluctuate as the stock price moved randomly. Their revolutionary idea was to continuously adjust the amount of stock held in the portfolio in such a way that the randomness in the stock's movement would perfectly cancel out the randomness in the option's value. They sought to build a riskless vessel to navigate a stochastic sea. This is precisely where Ito's lemma became the indispensable engine of discovery. The option's price, let us call it V, is a function of the stock price S and time t. To understand how V changes, one must apply the rules of Ito's calculus. Applying Ito's lemma to the function V of S and t yields a new stochastic differential equation for the change in the option's price, dV. This equation, like the one for the stock, contains a deterministic part and a random part proportional to dw sub t. The brilliance of the Black-Scholes-Merton argument lay in constructing their portfolio and then choosing the amount of stock to hold, a quantity known as the option's delta, to be exactly equal to the partial derivative of the option price with respect to the stock price. With this specific choice, a miraculous cancellation occurs. The random term in the equation for the option's changing value is precisely neutralized by the random term from the changing value of the stock held in the portfolio. The result is a portfolio whose value changes in a completely deterministic, risk-free manner. In an efficient market, any such risk-free asset must earn exactly the risk-free interest rate, the rate one could get from a government bond. Setting the return of this cleverly constructed portfolio equal to the risk-free rate, and performing the requisite algebraic simplification, causes the original drift rate of the stock, the Muddew term, to vanish from the final equation. This is another profound consequence. The option's price does not depend on the expected return of the stock, a notoriously difficult quantity to estimate. It depends only on its volatility, sigma, which can be reasonably inferred from historical price data. The final result of this chain of reasoning is a partial differential equation, the famous Black-Scholes equation. It relates the rate of change of the option's price with respect to time to its rates of change with respect to the stock price. Solving this equation, subject to the known value of the option at its expiration date, yields a single, unique, and theoretically sound price for the option at any prior time. It was a moment of breathtaking intellectual synthesis. The abstract machinery of Ito's calculus, born from pure mathematical curiosity, had provided the logical foundation for pricing financial uncertainty. The impact was immediate and transformative. The 1997 Nobel Memorial Prize in Economic Sciences was awarded to Merton and Scholes for this work. Black, having passed away, was ineligible but acknowledged as a core contributor. Their formula provided a standard, a benchmark against which options could be priced, hedged and traded. It catalyzed the explosive growth of the global derivatives market, which has since swelled to encompass hundreds of trillions of dollars in notional value. It turned the trading floors from arenas of intuition and gut feeling into domains dominated by physicists and mathematicians, the quants, armed with stochastic differential equations. The triumph in finance, however, represents just one application of this versatile language. The same class of equations Ito taught the world to solve appears in entirely different contexts, demonstrating the deep structural unity of random processes across nature and society. In population genetics, stochastic differential equations model the random drift of gene frequencies in a population under evolutionary pressures. In molecular dynamics, they describe the jiggling path of a protein as it folds or a particle buffeted by thermal noise. In engineering, the Kalman-Busse filter, a cornerstone of modern control theory used in everything from satellite navigation to signal processing, is itself the solution to a stochastic differential equation, providing the best possible estimate of a system's state from noisy measurements. In each case, Ito's calculus provides the essential grammar for translating a problem involving randomness into a tractable mathematical form, allowing for prediction, optimization and control. The financial revolution was simply its most conspicuous success, the first clear signal that a new and powerful way of reasoning about an uncertain world had arrived. The widespread adoption of Ito's calculus across disparate fields demonstrated its immense utility as a universal toolkit for modeling random evolution. Yet for Ito himself, and for the deeper currents of mathematics, a more fundamental question remained. His calculus provided an exquisitely precise description of the local, infinitesimal behavior of a random path. The Ito integral tells us how to take the next tiny uncertain step. A stochastic differential equation assembles these steps into a trajectory. The intellectual challenge that occupied the later part of Ito's career was to understand the consequences of these random steps on a global scale, to grasp the geometry of the universe of all possible outcomes. The task was to elevate the perspective from a single wandering particle to the transformation of an entire space under the influence of a random field. This required a formidable synthesis of his own probability theory with the classical deterministic world of differential geometry. His investigations led to the theory of stochastic flows of diffeomorphisms. A diffeomorphism can be pictured as a smooth, well-behaved deformation of a space, a stretching, twisting or compressing that preserves the essential geometric character of a manifold without tearing or gluing. Ito conceived of a flow where the deformation itself evolves randomly over time. Imagine a fluid covering a surface, where every particle of the fluid moves according to its own random buffeting. A stochastic flow describes the collective motion, the way the entire surface is churned and remapped by this sea of uncertainty. This framework provides a profound geometric interpretation of the solutions to stochastic differential equations. It shows how a random process acts not just on a point, but on the fabric of space itself, inducing a random evolution of its geometry. This work forged a deep and essential bridge between the worlds of Riemann and Wiener, demonstrating that the elegant structures of differential geometry could be extended to accommodate the dynamics of chance. It was the natural and necessary culmination of his life's work, a theory that described how smooth manifolds behave when subjected to the persistent creative force of noise. For many decades, the staggering implications of Ito's work were appreciated primarily within the specialized communities of probability theory and pure mathematics. He remained a quiet, unassuming figure at Kyoto University's Research Institute for Mathematical Sciences, dedicated to his research and to his students. The explosion of quantitative finance beginning in the 1970s, powered by the Black-Scholes-Merton equation, was the first event to thrust his name into a wider, more public sphere. Suddenly, Wall Street and the City of London were, however, unknowingly running on Ito calculus. This practical success catalyzed a broader recognition of the theory's foundational importance across all of science and engineering. The culmination of this long-overdue acknowledgement arrived in 2006. At the International Congress of Mathematicians in Madrid, Kiyosi Ito was named the first-ever recipient of the Carl Friedrich Gauss Prize. This award was specifically created to honor mathematicians whose work has had a profound and lasting impact far beyond the field of mathematics itself. In their citation, the committee celebrated his work for laying the foundations of stochastic analysis, a theory that has become an indispensable tool for understanding phenomena in the mathematical, physical, biological, and economic sciences. Standing before the world's mathematical community at the age of 90, Ito accepted the prize with his characteristic humility. The moment was a powerful testament to a lifetime of quiet, persistent, and revolutionary thought. It was the world finally catching up to the paradigm he had inaugurated more than 60 years prior. The ultimate significance of Kiyosi Ito's contribution, however, resides at an even deeper conceptual level. His work provided more than a collection of powerful techniques. It furnished science with a new language, a grammar for a world governed by intrinsic uncertainty. The majestic frameworks of Newtonian mechanics and Einsteinian relativity had given humanity a deterministic vision of the cosmos. In that clockwork universe, randomness was an artifact of ignorance, a statistical nuisance arising from incomplete information, a noise to be averaged away or filtered out. The underlying reality was presumed to be exact, predictable, and governed by immutable deterministic laws. Ito's mathematics offered a radically different perspective. It provided a rigorous and precise way to describe systems where randomness is a fundamental and irreducible element of reality. His calculus allows us to write down the laws of motion for the unpredictable. It embraces noise as a driving force of change, a source of dynamics and complexity. The Ito integral, the stochastic differential equation, and the geometric theory of stochastic flows form a complete and coherent intellectual edifice for analyzing probabilistic dynamics. This framework has enabled a conceptual shift in science, allowing us to see the elegant mathematical structures hidden within phenomena that once appeared to be nothing more than formless, intractable chaos. Kiyosi Ito taught us how to listen to the mathematics of chance, to find the subtle and beautiful equations that govern the jiggling of a pollen grain, the flicker of a stock price, and the random drift of genes through generations. He gave us the grammar to speak with precision about an uncertain world, and in doing so, he irrevocably altered our understanding of the very nature of change itself.